Okay, so the question proposed here is consider tablets that are contained in a blister package composed of a flat lidding sheet and a second form sheet that includes troughs to hold each tablet. The form sheet is 50 micrometers thick and is fabricated of a polymer material. Each trough is of diameter 5 millimeters and of depth 3 millimeters. The lidding sheet is fabricated of aluminum foil. The binary diffusion coefficient for water vapor in the polymer is 6 times 10 to the negative 14 meters per second, while the aluminum may be assumed to be impermeable to water vapor. For molar concentrations of water vapor in the polymer at the outer and inner surfaces are here, they're given respectively, and determine the rate at which water vapor is transferred to the trough wall to the tablet. So with any transport problem, whether it be momentum, heat, or mass transfer, you want to start with drawing the schematic of your system, which is what I did here. This is a lidding sheet. This is a formed polymer layer. There are blisters here. As you can see, it looks like a hemisphere. So that's going to lead us to the next point, which is picking a coordinate system. We're going to want to use spherical coordinates here. And we're going to want to pick our control volume, which is just like this semi-annulus here, this half annulus. This is our control volume. Next, you want to write down your constants. You have your diffusion coefficient and your boundary conditions given, CAS1 at our outer, CAS2 at our inner. And now we want to list our assumptions. So since this is a mass transfer problem, we want to list mass transfer related boundary conditions. So there's or assumptions, sorry. There's no homogeneous or heterogeneous reaction. We're using spherical coordinates, and it only occurs in the radial direction. It's actually symmetric, which means just symmetric in the theta and the phi direction. And this is the most important assumption. The next one is that it's pseudo-steady state, which means that the amount of time that it takes for this trough to become fully saturated with water vapor, the time scale for that to occur is so much longer than the time scale for diffusion of water vapor diffusing through this layer. That is essentially constant. So now you want to write down your conservation equation, which is your species conservation differential equation, species balance. And so this goes to 0, this time derivative, because of the pseudo-steady state assumption. This reaction term goes to 0 because we assume there's no homogeneous reaction, which is a valid assumption. Now we're left with the gradient in flux equals 0. So this means that there's a constant flux, which also confirms the pseudo-steady state assumption. Now you want to write down your constitutive equation, which is fixed rate equation. And so now we can simplify this even more because this term goes to 0 since it's dilute, it's diffusion through a solid. So this term accounts for convective fluxes. We're not going to have convective flux in a solid. And 2, because this water vapor diffusing through a solid is very dilute, so this mole fraction is close to 0. So this whole term can just go away. Now you're left with the typical fixed rate law, or not rate law, fixed first law. So you plug this into your equation here. Now you're left with your differential equation, your governing equation. Now, since you have 2 derivatives here, you're going to want to integrate twice, which means you have 2 integration constants. For 2 integration constants, we have 2 boundary conditions, one at our outer and one at our inner. And so to solve for these integration constants, you're going to want to solve both of these equations. So the easiest method that I saw was subtracting the second equation from the first to solve for A. This is what you get for A. Now you want to plug this into one of these equations. I plugged it into one. It doesn't matter if you plug it into 1 or 2. And you use that to solve for B. Then you want to plug in the integration constants back into your concentration profile to get this equation here. And then to check this equation, plug in our outer and see if you get CAS1, and plug in our inner and see if you get CAS2. If you do, you're gold. You have the concentration profile. Now we want to find the flux, because the flux is going to point us in the direction of the rate at which water is entering the pocket. So flux is negative DAB dCA over dr. I left out the negative sign here. I can explain this in the next slide. And then to determine the rate of water vapor reaching the tablet, we want to do a mass balance, because this is like a lumped parameter, essentially, analysis here. So accumulation equals in minus outlet generation minus consumption. Well, it's only going in. So the rate, this accumulation is the rate at which water vapor is entering the tablet. equals the flux evaluated at the inner surface times the surface area of the inner surface. So next, you want to plug in dc over dr, and I already did evaluate the r inner. So the small r that I have in the flux equation is r inner. And so since it's squared in this equation, the r inner cancels with this, and this is just r inner like this. So you want to plug in your numbers that you have. Make sure to convert to meters, everything to meters. That way the units add up. So always make sure the units are correct. And now you're left with this flux here, which is negative. But the reason why it's negative is because you're going in the opposite direction of your coordinate system. So we define this as R1 and R2. This would be R0. So the coordinate system increasing in this direction, but the flux is going against that, so it's negative. But to calculate the rate at which water is entering the system, you don't want it to be negative, so just use the absolute value of this. And the surface area is calculated 2 pi r squared. This is just half of the surface area of a sphere, evaluated at r inner, and then you plug it into this equation, get the rate, and it's 0.065 micromoles per day. It's not much water vapor at all, which is good to see. If you need any more help, please send me a message. I hope that helps.